In this video, we'll be creating an intake manifold for a Honda K24 swap. Hey everyone, this is Matt with Learn Everything About Design, and in this video, we're going to dive into some more car parts that we haven't seen yet, specifically into an intake manifold. Now, there are so many different manifolds out there on the market for different cars, but obviously we like to design parts in 3D and we want to make them. So what we're going to be doing is we're going to be creating an intake manifold based on a Honda K24 or K20, and this is going to be a rear-wheel drive swap. So we're not going to be using any of the stock Honda manifolds that are designed for front-wheel drive cars, but instead we're going to make one for rear-wheel drive. Now, this is a long-term project of mine. If you don't know, I'm working on a Mitsubishi Starion, and I am planning on doing a K24 swap into that car. I love the car. I've had it for a long time, but the stock engine is just old technology. Even back in the 80s, the engine was fairly ancient, and in order to rebuild it, I have two of them in order to rebuild the engines and to actually make decent power out of them. We still have to do things like create custom intake and exhaust manifolds, update the electronics, and at the end of the day, I think it's just better to get a more modern engine that's roughly equivalent in size and just make it work so that the car is more enjoyable. And I know a lot of people K-swap different cars. There are kits for S chassis, there are kits for Miatas, but my plan is to do a K-swap using the stock transmission. We'll have to design an oil pan, we'll have to design the exhaust manifold for a turbo, of course, and we'll have to design an intake. So this is not going to be a final intake by any means. I don't actually have a K series head or anything to reference. So what we're going to be doing is we're walking through the process of designing. We're going to talk about some considerations along the way, things like the tools that you have for fabrication, how you're going to make the parts, and then we're going to get into the design process. So to get this started, you can download the data set from the description below. And what I've done, if you want to start from scratch and follow along, is I went online and I got an image of the intake manifold gasket. Now, since I don't actually have one to measure, and what I've done in the past when I've been making intake plates or exhaust plates is I've actually gone through with a head off of a car and I've accurately measured everything using digital machines, a CMM or something that was fairly precise. But we don't have that in this case, and a lot of people don't have access to that. So what we're going to do is we're going to take a picture of an intake gasket. So you can search online, find your local parts store, you'll find a gasket like this. And as long as you've got a good shot like this, where we're looking at it straight, then what we can do is we can go to our canvas, we can right click and we can calibrate it. So for example, if you know the size or the width of the port, so if we're going from here to here, we know that that's about 50 millimeters. Then we now have our intake gasket scaled to the appropriate size. Now, we can't sit here and measure it because we don't actually have points to pick up from, but what you can do is you can check the calibration again. And for example, we know that these are 8mm bolts. You can see that the hole is a little bit over 8.5. So obviously we're dealing with a pixelated image. I'm going to hit escape to undo that, but we're dealing with a pixelated image, so it's not going to be perfect. But if we design everything parametrically and we make sure that we reference specific dimensions and make all the holes the same size, all the ports the same size, and so on, then what we can do is once we have that final data, if we actually get a head or a gasket to measure or something, then we can come back and we can actually put those different dimensions in there. Now, I'm planning on doing this in a series. We're not going to get through the entire intake in this video because there are a lot of parts that we need to consider. A lot of times when you're building an intake, you end up buying certain pieces. You buy the flange, you might buy a throttle body flange, you might buy the runners, they're all kinds of different pieces. And I think what we need to do is we need to level set the different builds or the different levels of builds based on the technology that we have available. Now, the most common sort of DIY intake is going to be something called a log plenum or a log manifold. Now, this style of manifold is typically done when you have round ports, because those are obviously the easiest to work with. But typically what you have is you will end up with a round piece of aluminum tubing that you can just drill holes in for your plenum and you can weld them. You can put a plate on the end for your throttle body and you're pretty much done. Obviously, you have to put some ports for things like the map sensor, air temp sensor, and things like that. But for the most part, it's the most simple, straightforward DIY version, assuming you have a TIG welder and you can weld aluminum. Now, there are more advanced solutions where you end up having CNC machined port matched runners and different flanges. You can even go as wild as doing hydroforming the actual plenum in pieces, and I will talk about that as well. And also just doing complete CNC, doing this in a couple pieces and either welding it together or bolting it together. So keep in mind that there are different levels to this based on your available tools, the technology that you're familiar with, and so on. But I plan to talk about sort of each of those along the way, maybe the benefits, the pros and cons. Obviously some of it's going to be bling factor, but there are benefits to doing things like a full CNC built intake, because you can do things like put dividers and runners on the inside to help direct the flow. When we're talking about boosted applications, there are important considerations as well. We want to make sure that we think about things like the plenum volume. That's going to be important. We also need to think about the flow, but it's not as important as it is on a normally aspirated car. So if we're building a turbo application, especially if you're doing a swap like a K-swap, generally the biggest consideration that you're going to have is avoiding the brake booster or clearing something else that's in the engine bay. We're not going to get down into that nitty-gritty detail because I really just want to talk about building something, and we're going to start from sort of the lowest hanging fruit. So in this design, what we have here is we've got a plane that has been created for the throttle body reference. So what I did was I created a line which was the width or the diameter of the throttle body, in this case 65 millimeter Ford Mustang throttle body, fairly common. You can find them pretty cheap online. But what I did was I decided where that needed to be relative to my origin, which I set at the center lower bolt for the intake flange. Then I decided how far away that was going to be. Then what I did was I created a sketch to represent the throttle body. Now, we haven't created any solid geometry yet. The reason I didn't show this is because this is pretty straightforward, and really it comes down to planning where the throttle body needs to be relative to the plenum itself. Now, the reason that I did it this way, and if I right click and show the dimensions on this sketch, the reason I did it this way is because I can decide that I need to push this up or bring it back down, or I can move the plane. Let's say I wanted it to be 175 out. I can move these values and I can tweak them even after we start creating solid geometry. So if we're really careful with how and where we dimension everything, not just the sketch here relative to our plane, but if we're careful how we dimension all of the different solid bodies that go together, then we can build something that can be configured fairly easily. Now, I don't have the throttle body tilted in at an angle. Generally, you will see Honda intakes will be pointing a certain direction. For my application, it's going to have a front mount intercooler, and I will probably end up, when I design my final intake, I'll probably end up tilting the throttle body down, but I'm not going to be doing this sort of log or cannon style intake. So again, we're starting from the basics. We're starting from sort of the lowest hanging fruit. So what I want to do from here is start to build out some solid bodies. And in Fusion 360, there's an important thing that we need to think about, and that's bodies and components. Now, generally what you would do is, for a design like this, all the parts are going to be welded or stuck together. And when that's the case, you really don't have to choose bodies or components. You can just start building with bodies. One of the benefits to creating things out of components is going to be that we can separate out all the sketches and features and easily organize them into components. That's one aspect of it. For making things like detailed drawings, we have a much easier time creating exploded views if we want to separate the runners from the flanges. Another aspect of this is that downstream, one of the versions that we're going to talk about is going to be sheet metal. And sheet metal requires us to create a sheet metal component. So I know that downstream from this, we will have to have a sheet metal component. So for me, it just makes the most sense once I start creating these solid bodies and even more sketches that I want to do this at the component level. So this design already has a component in it. It's called head flange. And what we're going to do is we're going to talk about how we create those components, and again, a little bit about why. So first thing I want to do is I'm going to go ahead and save this design. I don't want to lose anything. I really haven't done anything yet, but it's always a good idea to make these saves because in Fusion, we always have that version that we can go back to. And again, it's important to remember that you can go in the description of the video and you can download what you see here, which will include the canvas for the gasket. It'll include the two sketches I showed, the TB reference plane and the throttle body, and it will include this empty component called head flange. So in order to make a component in Fusion 360, it can actually be done a handful of ways. When you are creating a new feature like an extrude, there's an option to create a new component. Now, while you can do it on the fly when you're creating something like an extrude or a revolve, there is a negative side to doing it that way. The negative side is that the sketch used to create that feature, in this case a sketch for an extrude, that is going to live at the top level of your design. You'll notice there's a little radio button next to the very top level. Because we want to use this method to contain everything, the best way to do this is for us to create a component first. Now, you'll notice that in this example, I've already created my sketch for my throttle body and the TB reference plane. So you can see in the timeline, we've got the reference plane, we've got a plane that's created, and we've got the throttle body sketch. Now, in reality, I want to have a component for the throttle body plate, so I would want to make sure that I created that first, but I already have the sketch here. So how do we go about this? Well, there are some ways to configure this in Fusion 360. You can drag and drop things around. You can roll the timeline marker back just like I did. And what I'm going to do is I'm going to roll that back. I'm going to create a new component, and I'm going to call this TB plate. And keeping in mind that components can be standard or sheet metal, in this case we want standard, we also can have them external or internal. Now the difference here is that external will be saved in your data panel as a new design, and it'll have an external link. For our intake design, if we were going to be using or reusing the throttle body plate over and over again on different intakes, it might make sense for us to save it externally. If we're just going to be designing everything in context of this assembly, we can keep it internal. So in this case, I'm going to keep it internal. But again, if you were going to reuse that plate over and over again, in reality, you'd probably model it in its own design and then just bring it in. The next thing that we want to think about is the parent. Now, we want the parent to be the top level of the design. Otherwise, it's going to be a child of any component that's currently active. So keep in mind that the current active component oftentimes will get inherited as the parent. So you want to make sure that if you are inside of, say, the head flange component, that you deselect the parent and then you manually select which one you want. And then we have this activate option, and that's going to automatically enable the component that we're working on. I'm going to deselect that option for now and say okay. So now we've got our head flange and we've got our TB plate. These don't contain anything other than their own origins. And the reason why they contain their own origins is because Fusion 360 keeps track of this relative to the top level origin. This is how it gets away with mechanical motion. When you apply a joint or an as-built joint, it takes a look at the location and the orientation of the coordinate systems relative to each other. When you set things like the pivot point in a joint, it knows exactly where that pivot point is in relation to everything, and it translates it relative to the top level origin. So it has to have its own origin, but other than that, nothing else is really needed. If you're interested more about making use of joints and components, you can take a look at some of the videos that I did on creating suspension geometry and how we can use this relationship of different components and their origins to take a look at creating suspension without actually having to design anything. If you're just planning out the locations of things like the steering pivot location or the upper and lower A-arms. You can make use of designing those pivot points as a sketch, and then you can just use joints until you get to the point where you want to design those solids. With that out of the way, let's hop into how we can handle getting this sketch into the TB plate. So what I want to do and what I want to think about is the fact that my TB sketch is on this construction plane that we created. Now the construction plane was created outside of this new component. We can see that the TB plate component is in the timeline. Now I promise if you are familiar with Fusion and you already know all this, we will get into modeling stuff here soon. But I think that this is important because a lot of times when people get started designing stuff in Fusion, they really don't understand the bodies and components and what that does or how that affects downstream. So let's see if we can get this sketch into our TB plate. So I'm going to drag and drop the timeline to the end, and notice that the sketch is inside of the top level. If I take this and I drag and drop it into my TB plate, I now have a sketches folder that's inside of my TB plate. This only works because the sketch was after my component creation in the timeline. So if I happened to have it before that, it wouldn't have worked. We can drag things back and forth around inside of the timeline itself, but there is going to be a certain limitation. If you're referencing something that happened earlier or later in the timeline, then oftentimes that'll be sort of the kickoff or the inception point for the parent-child relationship. Now that the plane was created after the fact, I could also move the TB reference plane, and I could drag the TB reference plane into my sketches folder inside of this component. But you'll notice that when I try to do this, it instantly moved the construction plane into that component as well. So this gets really tricky as soon as you start creating solid features and adding things like fillets to corners. Then you really start to have a lot of complications with dragging and dropping things around. This early in the process, you can get away with it and not have to redo your work of redoing the sketches and redoing all that stuff. But that's why I wanted to start here, so we could understand not only the implications of creating those components first, but also how we can reorganize it. So now if I activate the head flange, you'll notice there's nothing in my timeline. No sketches have been created because this canvas was done at the top level. However, if I activate the TB plate, we can see that the sketch for the reference of the plane itself, as well as the throttle body sketch are all listed in the timeline when my TB plate is active. Go back up to the top level and everything in the design is listed again. So again, once our designs become really complicated and we start to add tons and tons of detail, if we have dozens or hundreds of components, starting from scratch from a component is really going to be that important kickoff point, just because it really helps find things in the timeline. Another really important aspect, and then I swear I'm going to move on, is renaming things inside of your inside of the components or bodies or sketches or whatever you're designing. Renaming these and even renaming the features. You can rename any of this stuff down here by right-clicking on it and renaming it. You can also do it by right-clicking on the sketch or just double-clicking on it. So, well, if you fast double-click, then you're going to edit the sketch. But if you slow double-click on it, you'll be able to edit the name. And that's really important as you start to create complex designs. And I'll say that I'm guilty of not doing it very much or not doing it enough. It really just depends for me what the intent of the design is. If I'm doing a bunch of concept work, I generally don't care. If I'm creating a design that I know is going to get manufactured or I know somebody else is going to be working with, then I'll take the time to do things like name my sketches, or at least the critical sketches, name features. I will create groups of features in the timeline by selecting multiples, right-clicking, and creating a group. These are all things that are important for the organization of your design. All right, so now that we got all that said, let's do a quick save, make sure we don't lose anything. And now's the point where we're going to start creating some solid bodies. Because the throttle body flange already has a sketch, and because it's essentially because it's easier, let's go ahead and start with that by activating the TB plate. I'm going to show the 65mm throttle body sketch, and then I'm going to create an extrude. And when we create an extrude, we just simply need to select the profile we're interested in. And then we need to give it a dimension. Now you'll notice that all this is in metric, and that's just because, well, partially because the intake plate and the ports and the dimensions for things like the reliefs that we're going to have to make for the 14 millimeter injectors, all of those are in metric values. But if we want to use an actual imperial measurement, let's say that this plate we're going to get cut is 3/8 or ½ inch thick. A ½ inch is pretty extreme, but if we're going to say that this is 3/8 thick, notice that it's in the negative direction. We can say minus 3 divided by 8. Now, it's automatically going to be 3/8 of a millimeter, which is tiny. But if we just put IN or INCH after it, then it'll automatically convert it to inch. Now, you'll notice nothing's happening yet, and that's because we need to put a space between the 3/8 and the inch. And oftentimes, when you get these red numbers, it's hard to understand why. And part of the reason is because if we look in the distance over here, it's multiplying it by 1 millimeter automatically. Now, anytime you begin to type something in and you let it figure out what it is, the preview on the screen, then it's already sort of committed itself to a units. So it doesn't show the times 1 millimeter here on the screen, but if we want to override that, we actually have to multiply it times 1 inch, or we can manually update the mm to inch inside of the distance dialog box. Now, if you do it quick enough, it doesn't matter. And if I'll go ahead and I'll just do this again. Minus 3 divided by 8, and I put IN in here. I can sometimes catch it before it actually goes and turns it into metric. But if you ever run into this where it just doesn't look like it's updating properly, then just make sure that you come over here and you reset the units as inch, or again, you manually enter that value. So with that said, let's go ahead and say okay. And now that we have this flange, we're just going to add some fillets to the corners. So when I look at it from the left, obviously we don't want something square. We could spend a lot of time going through and making this look nicer and having an offset of the inside. But honestly, if you're doing a DIY, you are probably going to end up cutting this with a hole saw through the center and probably with a bandsaw on the outside. And we all know that we don't want to spend a ton of time trying to make something that perfectly matches a sort of a weird contour. So for this example, I'm going to just fillet the corners of this plate, and I'm going to keep it nice and square. What we're going to do is, again, we're going to add an imperial value. I'm going to say 0.25 IN. And in this case, it updates fine. And part of the reason is because we don't have a fraction in there. Once you add the operator of a fraction, you're dividing 3 by 8, then automatically it becomes a mathematical operator, and Fusion in the back end, which all the units are centimeters, Fusion in the back end throws up a flag and says, all right, well, we automatically need to multiply this by 1 millimeter. If you don't have that fraction in there, then doing the inch conversion is quicker and easier. So this is pretty straightforward. I do know that depending on the throttle body that you end up using, sometimes they have a little relief notch that needs to be cut for things like the throttle linkage, if it's got a mechanical linkage on it, or maybe there's an air sensor or something on the side, or throttle position sensor. So just keep in mind that we are going very basic here. This dimensionally fits a 65 millimeter throttle body, but please don't take what we're modeling here and go start producing it without checking your own numbers. That's going to be real important, because right now what we're doing is we're concepting. So if you're going to be actually manufacturing something, please take the time to make sure that you do measure everything you need. Okay, so now that we have this, I'm going to activate the top level again. Notice that everything that we've done has been created down here. So you can see our sketch, our extrude, and our fillet. Now, something that we should keep in mind is that even though we planned out the TB reference plane and the sketch location and the construction plane, because we have components, remember that the origin is going to be referencing or related to the origin in the top level of our design. Now, the plane that we referenced, the construction plane, is off here in space relative to the origin, and that's how I defined it intentionally. A lot of times, if you're designing a new part, it's going to be centered at the origin because you want to make use of symmetry. Now, when we have a design like this, where this part is seemingly floating off in space, keep in mind that Fusion is still keeping track of the location of these coordinates. So if I move this around, you can see that the coordinate system that's relative to our throttle body plate is moving relative to the top level origin. Now this is important because this is how Fusion keeps track of the location. If I capture its position, we now have a capture position feature in the timeline. If I select that and delete it, it's going to put it back where we are initially referencing it. I can also revert the position. So when we create something like a joint for mechanical motion, again, what Fusion is doing is it's saying, well, I know that this coordinate system is this distance away from coordinate system. I know that X is pointing this direction, and I know that it's supposed to rotate relative to this axis. So when you make those joints, just think about that relationship and what you're actually doing. Now, there's no reason to really worry about any of this stuff moving, because anytime that we have something that is moving around, Fusion is going to ask us to capture its position or revert its position anytime. Even if I come in here and move this and I try to start creating an extrude, it will say, hold on, wait a second, things moved, we need to know where they are. So we can revert or capture the position at any time. So keep in mind that you don't really have to worry about locking things down. If you want to, you can right click on the component and you can ground it. But keep in mind that ground is a feature in the timeline. So if you want to unground it, you can either delete that or you can right click and unground it. But again, keep in mind that unground is a feature in the timeline. So for a case like this where we don't really care about these things moving because we know that we're going to revert the position, I'm going to go ahead and leave it. When I have parts that rotate around, oftentimes I will ground one of them because we need a base to make sure that not everything moves in space. So in this case, again, not a big deal. You can ground it if you want to, but the reasoning behind it is because Fusion wants to know exactly where our coordinate systems are. Right now we don't care. We know where they're supposed to be. We'll revert the position. Let's do a quick save to make sure we don't lose anything. And let's go ahead and activate the head flange. Now you'll notice when we activate the head flange, the canvas of the head gasket changes opacity. Now the reason it changes opacity is because it belongs at the top level of this design. Whereas when we activate the head flange, the opacity of everything else changes. The opacity of our throttle body flange, the opacity of the canvas, and anything that belongs in any other component or at the top level. So again, these are things that we need to think about. Now, the benefit here is that canvases don't really reference anything. We can edit the canvas and move it around, do whatever we want. So all we really need to do is make sure that it happened after the creation of that component, and then we should be able to drag it into this component. Now, it gets a little bit trickier with canvases because of the way that they behave and the way that they belong. Sometimes you might end up having to actually roll all the way back, activate the head flange, and then try to go forward. It doesn't always work. Sometimes you might actually have to re-import the canvas. But again, it's not quite as easy as a process of moving things like sketches and features around. One of the ways that we can help this is we can right-click and edit the canvas, and we can increase its opacity to 100%. So that way when we activate the head flange, the opacity change isn't as drastic for us. I'm going to hide the throttle body plate for now because it really doesn't need to be seen. And I'm going to start creating a sketch. Now the canvas was placed on an origin plane, but remember our components have their own origin planes as well. Because they're in the same location, then all we really need to do is just select the XZ plane or the front plane. With something like this, I always try to make sure that one of the bolt holes or one of the ports is centered about the origin. You can see that we're pretty close here. It's not exact, but again, we're looking at a picture of a gasket, so we're only going to get so much precision. So I'm going to start by creating a center diameter circle here. I'm going to use my dimension tool, which is D on the keyboard, and I'm going to make this 8.5 millimeters. So that one is fully defined. Next, I need to create the holes for all the rest of the stuff. You'll notice that there is a recess in this gasket and there are some holes in here. Now, again, I don't have a K24 yet. I don't have one of these heads. If you guys know exactly what these ports are, then you can share and please let me know. Generally, these are either EGR ports, so they'll be exhaust gas or circulation. They might feed coolant passages, but I'm pretty sure on this head the coolant passage is at the front of the block next to this. So if you know what those are, please let me know. I don't know if they're even used on this block for anything, but I am not going to be modeling those. I'm only going to be modeling the bolt holes. So next, I'm just going to go ahead and place a couple other circles where these holes are and get them relatively close. And again, I'm not worried about all of them. I'm only worried about the ones that are directly around those ports. And then I'm going to use equal. Now, keep in mind when we use the equal constraint, we are going to be making them equal to this original bolt. Now, if I just work my way around and I select this one and move around, that means that if I delete or change this hole at any point in time, then the reference is broken. So what I like to do is I like to always make sure that I go back to the original. Now, unfortunately, that means we're going to have a ton of these equal constraints displayed around this hole, but it becomes a little bit easier for us just because we can go back to that single reference point. So again, equal between these two. Now all the diameters are right. The next thing that we need to think about is how we're going to define their heights and their locations. Now it appears to me that these holes here are horizontal relative to each other. And it appears to me that the flange has symmetry. So I'm going to make use of that by first creating a line from the origin or the center of this hole vertically. I'm going to hit escape. I'm going to make that construction. You can also hit X on the keyboard if you want to convert lines to and from construction. The next thing I'm going to do is take a look at my symmetry constraint. Now when we have a symmetry constraint, there are three selections it's looking for, even though it doesn't say this on the screen. We're going to select the object here on the left side, the object on the right side, and then the mirror line. We're going to do the same thing here, left, right, mirror, left, right, and mirror, and then I'm going to hit escape to get off the constraint tool. Now this is the same thing that ends up happening when we use something like mirror, because essentially mirror just copies it and adds this constraint. Now you will notice that last hole is not actually a mirror of this one. The bottom ones seem fine. This one here is also not in the same position. You'll notice it's kind of in between these two. So I'm going to use Control Z to undo the last two symmetries. So even though they look symmetric, they are not because the position of these holes. So again, something for us to keep in mind that we want to make use of symmetry when possible, but it's not always the case. I will say that these holes, at least these two here, do look like they are horizontal with each other. However, these two do not. This one is obviously up higher. So we're going to hit escape to get off of that. And now that we've got our constraints defined, let's go ahead and start adding some dimensions. Again, we are dealing with a gasket, so we can only get so precise. But first, let's go ahead and add a horizontal dimension here. It looks to me that it's about 128 millimeters. And it does not look like it's exactly horizontal. It looks like it's just a little bit below. But again, we are dealing with the gasket. You can see this one looks like it's slightly above. I don't know if it's completely horizontal. It could be the picture, but I am going to use a horizontal constraint and define it here. And you can see now that both of those holes are fully defined because again, we've got symmetry. Next, we need to start defining these holes up here. So again, dimension tool, I'm going to pick the origin as my reference. 66.5 looks to be about right. These are horizontal with each other. And then I want to get a horizontal dimension from this line. 96 millimeters. And you have to remember that when these things are designed, most likely they are using nice round numbers. Now, in most cases, that's true, not in all cases, but when you're dealing with something that's designed in metric units, you're not going to expect to see 96.235 millimeters. You're probably going to see 96 millimeters, 76, 8.5. So just keep that in mind. If you're making some assumptions, then probably stick with nice round numbers, at least at this phase, until you can actually get your hands on something to measure it. Next, I'm going to do the same thing over here. Looks like about 162. This one over here could be the same distance away. And actually it looks like 164, so pretty close, maybe 165. And 165 looks to be a bit much. 164.5. Looks pretty close, but I'm going to go back to 164. So again, we are dealing with a gasket. we are assuming that it is a perfectly undistorted picture, which obviously it's not going to be. But again, make sure that we fully define things and that we use a good reference point, in this case, our origin. Now this one looks about 63. I'm going to go again from my origin point. This one over here, 66.5. And now we've got the bolt hole locations fully defined. The outside of the plate, again, we can keep it simple and we can make it a rectangle. Something like this, you're probably not going to cut by hand. You're probably going to have water jet or laser cut. In reality, these plates are often CNC machined because of the port injection and the opening and the shape of these ports. Oftentimes they're a little bit more intricate. So we'll have to keep that in mind. I'm going to view this as a flat plate and assume that we would weld an injector bung onto the runner itself. Again, this is going to be the most DIY version. We will get into more advanced versions in future videos, but I wanted to at least start here. So before I worry about the outside, I want to define one of these ports. Now these are oval ports, so I'm going to use the slot first, and I'm going to use the center to center slot, and I'm just going to start from here to here and create a slot shape, and then hit escape to get off the slot tool. And then we can sort of move these things around and get it relatively close. Now there are some numbers floating around online. You can kind of, you can play around with the different sizes. We can move some of these points up and down. Again, we are dealing with a gasket. It's really best to actually measure something. But once I get it relatively close, I'm going to use D to dimension. And I want to find this point location. And 35 millimeters, again, nice round number. It's probably what you're looking for. 16 millimeters wide. We're going to give it a radius value. Looks like 17 is about right, maybe 17.25. And then we also need to define its height. So the center of it looks to be about 30 millimeters. And you can see that that's relatively close. Again, we're dealing with a gasket, but these are all nice round numbers, and this is what I would expect to see. 30 millimeters to the center line, 35 to the center point of the arc, 16 wide in the center, radius of 17.25. So again, these are all numbers that I would expect to see. Now, if you have actual port numbers, obviously you go with those. Next, I'm going to do a center diameter circle, keeping in mind that the midpoint of this, the injector port is likely going to be relative to that. So what we can do is we can take a line and we can draw it straight down to the midpoint, hit escape to get off of our dimension tool or our line tool, and then we can convert that to construction. So that makes sure that if we happen to move this port or change the port shape or size, so for example, if I took this to 18, you can see that this didn't move, and this line needs to stay vertical. So make sure that we adjust those constraints and those dimensions so that everything updates how we expect. So now that that's in roughly the right place, let's take a look at finding where that is. It looks pretty good. D, and I'm going to say 11 millimeters, and then I'm going to give it a height distance. This looks to be 7.25, and I'd say that looks pretty good. Now, the other thing we need to do is we need to define an arc. So we're going to go to Create, Arc, 3-point arc, and we'll just go from here to here and drag it until it's tangent. We're going to grab a tangent constraint, make sure that this is tangent with this arc, and I'm going to use my horizontal constraint. And I am going to, actually, you know what? Let's hit escape. Let's not use horizontal constraint. Let's drag this until it looks right. So once that looks about right, I'll hit D and I'll give it a dimension, 17.5 millimeters. Now, because we know everything is symmetric and this is relative to the midpoint of that upper edge, we can just mirror this to the other side of our vertical reference line. And what we're looking for here is to make sure that we have complete closed profiles. If we don't have a closed profile, that means that we don't have coincident relationship with this circle or this arc here. So as long as you can select those profiles, making sure that show profile is turned on, which is on by default, then it should be fine. Now you can see there's a little bit of gap. Again, we're getting as close as we can, and then you can always come back and tweak these numbers if you have an actual gasket or an actual intake or an actual head to measure. But this is the basic process of defining these. Now, we need to figure out if there is actually some sort of pattern to this. So if we go ahead and mirror, and we take all of these elements we just created, the slot, the arcs, and I'm going to go ahead and include the center lines as well, even though I don't necessarily need to. I'm going to go ahead and mirror those across, and it looks like it matches perfectly. Now, in reality, what I probably should have done was just created this one here, and then I could have just created a pattern, a linear pattern. But there are other ways that we can do this as well. We can use modify and move copy to create a copy of these elements and then push them to the certain distance apart. And sometimes what you want to do is you want to measure the distance between these centers. So for example, this position to this position is 86 millimeters on the nose. And that's going to be based on the fact that we dimensioned this a certain distance away, 35 plus 16, and this gives us our numbers. But 86 millimeters between these, so we could create a linear pattern, or we could do a move copy. So what we're going to do is we're going to select the objects. I'm going to say this, select everything that I want to pattern. I'll even go with these as well. And then we want to select our direction. It's going to be to the right, and we can pull this out. I only need 2 of these in this direction, and I'm going to pull it out until it's 86 millimeters. So manually enter 86 millimeters, say OK, and now we've got that full one there. And then we can just use mirror, select all the geometry we want to mirror. Again, I'm taking the construction lines. You don't necessarily need to, but I like to have them as a reference, so I want to make sure that they are there. And you can see that all of these ports appear, it's not perfect, but they appear to be symmetric in the fact that the stuff on the right-hand side looks to roughly match with the stuff on the left-hand side. Again, I can't imagine that Honda engineers would have this back left port 1 millimeter different, because then that messes up things like the cylinder sleeve spacing and the distance between for the cooling passages. So I'm going to assume that everything is symmetric left to right based on that centerline bolt, and I'm going to assume that everything is fine. From here is where you need to decide what you want the outside of this flange to look like. Do you want to try to match this gasket or just make a rectangle? For me, for this, again, basic example, I'm going to make a rectangle, but it's important to note, at least with this K series engine, that it really will not work as a rectangle on the right-hand side, partially because of the coolant passages. So unless you're going to incorporate the cooling passages into this flange, which you can do, then you're going to want to match this side over here. For us, we don't necessarily need to do that, so we can draw a rectangle just for this basic example. If you do want to match that, then it's best to use things like a spline and an offset. But again, keep in mind that most of this stuff is going to be based on lines and arcs, and you're not going to find a lot of these shapes that are done with splines or polylines. So just keep some of those things in mind as you're designing your own. But I'm just going to go out to about where the entire gasket is, and then I'm going to give it some dimensions. So from that origin point to the top, I'm going to say that it's 75.5 millimeters. I'm going to give it an overall height of 85 millimeters. I'm going to hit escape to get off of this for a second. And another thing that I think is important is that we really think about where these dimensions are, and so that way they're easily readable. So as you're designing these parts, and even though this is a sketch and it's not a detailed drawing, keeping these dimensions so that you can read them. Some of them you will have to zoom in, and obviously these constraints are really hard, so you can always hide those constraints to clean things up a little bit. But as you get started, just keep in mind that you should really make sure that the dimensions are easy to read. You'll thank yourself, or at least your future self will thank you when you come back to edit this. So now this left edge, I'm going to say from the origin, is 171 millimeters. And I'm going to give it an overall width of 347.5. So that looks pretty good. Now we can finish the sketch, and we should have a pretty easy time just extruding this. So again, I'm going to pull this out. I'm going to say minus 3 divided by 8. And then over here, I'm going to change that to inch, and I'm going to hit enter. So now we can hide the canvas, and now we can bring back our throttle body plate and we can activate the top level. So at a very basic level, we now have a flange at the head and a flange for the throttle body. This is going to be the starting point of our manifold. Now, I know that it took quite a bit of time for us to get to this point, but making sure that we take the time to define the locations of everything will make it a whole lot easier to change later. If you want to do things like shift where the throttle body is relative to the plate, it's very easy for us to do. We can come back to our TB reference plane, and now that we have this solid, so for example, if I change this to 250, it's going to move just fine. If I bring it back to 200, you can see everything moves according to my dimensions. If this needs to be closer because I don't have enough room, or if I have plenty of room and I want the runners to be a bit longer, you can see that it's very easy for us to move these things around. The 65 millimeter line, that is actually a factor, partially because the center line for the location of the throttle body is based off of this line. So I'm assuming a 65 millimeter throttle body. If we happen to go to 70 millimeters, then the midline of the throttle body is going to move over as well. Now, what I would do in reality, if I were designing these for manufacture, what I would do is I would create some user parameters to help drive some of these values. So things like the port sizes, I would come in to change parameters, and I would make a user parameter called TBDIA for diameter, and I would make that 65 millimeters. So what that does is it lets me take a look at this first one here, and this value, what I would say is I would link it to TB diameter. Now, the reason that that works well is because now I don't need to find those sketches. I can always go back to my change parameters. And let's say that I took this to 100 millimeter throttle body. It's going to move to the center relative to that sketch. 65, it puts it back. So again, this is where the pre-planning and forethought comes in. If you're designing your first intake, or if you're just getting into Fusion, then planning at that level is a downstream thing. It doesn't make or break a design. It just makes it easier to update later. So what we're going to do from here is we're going to save this. And in the next video, we'll come back and we'll start to talk about creating those runners, creating the runners for the ports. And we'll talk about dealing with things like the intake bungs. So those are going to have to be machine parts that get welded on. We're going to talk about creating the actual plenum volume and how that's going to attach to our throttle body plate. And we'll talk about all those different aspects of it. But at this stage, what we can do is we can just make sure that we saved. And if you're going to carry on with without the next video, then what I want you to think about is going to be off-the-shelf components. You need to be able to find oval tubing that matches your size. You need to be able to find a plenum tube, whether it's 3 inches or 4-inch diameter. Find a piece that you can actually use, because there's no point in designing something DIY that you can't actually buy the parts. Or you might find that a 3-inch diameter aluminum tube that you might use might be really cheap because tons of people use it on intakes. Intakes for intercoolers, or maybe it's used on exhaust tips, or maybe it's used for this or that. But 3 1/4 might be extremely expensive. So these are things that we need to think about. And if you're shooting for a specific volume, that's where you could say, well, this pipe is really expensive. So what I want to do is I want to make this plenum a little bit longer to get the volume I need. But we'll talk about that in the next video. But at this stage, make sure everything's saved. And if you have any questions, please let me know. You can always email me, support@cadeducator.com. Thanks for watching, and we'll see you in the next one.